Assalamualaikum warahmatullahi wabarakatuh. My name is Nanda Rizam and I will explain about part 1 and part 2. So in this slide, we have a topology design. For part 1, we designed the network topology using GNS3 to represent Skynet Industries multi-home BGP environment. So Skynet operates under autonomous system 65010 and uses two internal router which is R1 and R2. Each router connects to a different internet service provider to ensure redundancy and better availability. So router R1 is connected to ISP-A while router R2 is connected to ISP-B. An internal link connects R1 and R2 to allow internal communication within the Skynet network. A LAN network is connected to R1 to represent Skynet internal user which is PC-wide. So this topology ensures that if one ISP link fails, Skynet can still maintain internet connectivity through the second ISP. This is the IP address configuration table as you can see with different IP address for different interface. For LAN Skynet submask, we use fast internet 2/0 at router R1. The IP address is 192.168.10.1 and the net mask is 255.255.255.0. So now I will talk about part 2. So for part 2, an IPv4 addressing plan was implemented to assign IP addresses to all router interfaces, internal links, and ISP facing connection. So point-to-point link uses /30 subnets while the LAN uses a /24 subnets. The internal link between R1 and R2 uses the subnet 10.10.10.0/30. So on R1, first internet 1/0 is assigned the IP address 10.10.10.1. And the EBGP link between R1 and ISP-A uses the subnet 172.16.1.0/30. So R1 uses IP address 172.16.11. And the Skynet LAN subnet, Skynet internal LAN network uses the subnet 192.16.10.0/24. So router R1 is configured as the default gateway for the LAN with the IP address 192.16.10.1. This LAN represents Skynet internal users and is the prefix advertised to both ISPs. So the internal link between R1 and R2. On R2, first internet 1/0 is assigned the IP address 10.10.10.2. So the link is used for internal BGP communication within AS65010. And the EBGP link between R2 and ISP-B uses the subnet 172.16.2.0/30. R2 uses IP address 172.16.2.1. Just now, we already see the R1 and R2 configuration, and this is ISP-A and ISP-B configuration. So the EBGP link between R1 and ISP-A uses subnet 172.16.1.0/30. So ISP-A uses 172.16.1.2. And the EBGP link between R2 and ISP-B uses subnet 172.16.2.0/30. And ISP-B uses 172.16.2.2. This is the Skynet interline network use the subnet 192.16.10.1/24. So router R1 is configured as the default gateway for the LAN with the IP address 192.168.10.1. So this LAN represents Skynet internal users and is the preferred advertised to both ISP. So in summary, the topology and IP addressing plan provide a well-structured foundation for Skynet's BGP implementation. So the use of point-to-point subnet improves efficiency, while the LAN subnet supports internal enterprise connectivity.
Hi, Assalamualaikum. My name is Noor Amir Azwaris, and I'd like to continue to this slide. For this slide, we configure the IBGP, which is the internal border gateway protocol. So here R1 and R2 are in the same autonomous system AS, which is AS 65010. We use the router BGP command to define each router has a neighbor within the same AS. This allows R1 and R2 to exchange the routing information internally. Next, we configure the eBGP, which is External Border Gateway Protocol. In this case, R1 connect with ISP-A, which belong to a different AS. This remote AS command is used to specify the external AS number. This allows to RS to communicate routing information with ISP-A. And for this slide, we configure the other eBGP connections, which is R2 and ISP-B. R2 is still in AS65010, while ISP-B is in different AS. This ensures that R2 can exchange routing information with ISP-B successfully. Here, we advertise Skynet's internal network using the network command. The Internet Network 192.168.100 is advertised for both R1 and R2. This step is important so that the Internet network can be linked by the other BGP neighbor. This slide shows the output of show IP BGP summary on R1. From this output, we can see the BGP neighbors are in established state. That's confirmed that both iBGP and eBGP session on R1 is working correctly. Here, we show the IP route command on R1. The routing table shows connected network on BGP routes. This provides the R1 is successfully received the storing routes from BGP. This slide displays show IP BGP summary. Command on R2, the neighbors are shown as active and established. This confirms that R2 has successfully formed both internal and external BGP connection. Here, we use the show IP BGP command on R2. The BGP table shows the advertised network. The next hop. This slide shows the routing table on R2. We can see BGP route marked with the letter B, meaning they were learned through RBGP. This confirms that. Finally, we perform ping test to verify connectivity. The successful communicate properly.
For question 4, we implement the access control list ACL-based prefix filtering on both R1 and R2 to prevent the prefix hijacking. First, we create a standard access control list called Skynet prefix, which permits only Skynet's authorized network, which is 192.168.10.0. This ensures that only legitimate prefixes are allowed for the advertisement. Next, we create a route map named outfilter and match it with the Skynet prefix ACL. The route map controls which prefixes are allowed to pass through BGP updates. Finally, we apply the route map to the BGP process so that outbound BGP advertisements are filtered. This prevents any unauthorized or accidental prefix from being advertised to the external ISP. By using ACL-based prefix filtering, Skynet reduces the risk of prefix hijacking and improves the overall security of its BGP environment. What is prefix hijacking? Prefix hijacking happens when unauthorized autonomous system or AS advertises the IP address prefix that it does not own. When this happens, internet traffic that should go to the legitimate network is redirected to the wrong AS. This can cause a serious problem such as service disruption, traffic blackholing, or even data interception. Prefix hijacking may occur accidentally due to configuration mistake or intentionally as a malicious attack. Prefix hijacking occurs in BGP because of BGP is a trust-based routing protocol. BGP does not verify whether an autonomous system is authorized to advertise a specific IP prefix. If an external AS accidentally or maliciously advertises the Skynet's prefix, other networks may accept this false route as a valid. As a result, traffic destined for Skynet can be diverted away from a legitimate network, causing a connectivity and security issue. ACL-based prefix filtering helps to prevent the prefix hijacking by controlling which prefixes are allowed to be advertised through BGP. In this approach, an access control list is created to permit only authorized prefixes owned by the organization. The ACL is applied using a route map to outbound the BGP updates. This ensures that only Skynet legitimate prefix such as 192.168.10.0 is announced to the ISP, prevent the accidental route leaks and reduce the risk of prefix hijacking.